Hi, I'm Tiffany. I'm a grad student here at UC Santa Cruz, and today I'll be talking about my work with Ryan Cook, Mike Bolte, and X, searching for the lowest metallicity galaxies. So first, a bit about low metallicity galaxies. A galaxy is considered to be of low metallicity if its gas phase oxygen abundance is less than or equal to a tenth solar. And currently, some of the lowest metallicity galaxies known today have a metallicity of about 1/100th solar metallicity. And in the literature, these systems are known as blue compact dwarf galaxies, or BCDs, and historically as isolated extragalactic H2 regions, or Sargent-Surley objects. So BCDs are our closest analogs to the earliest galaxies in the universe, and this is because of their low metallicity and active star formation. And because they're nearby, they're close enough for detailed studies. And when I say nearby, I mean redshifts of 0.001 to 0.05. And what I'm particularly interested in is using the near pristine gas in these systems to better study and constrain primordial abundances as created during BBN. And particularly, I'm interested in primordial helium-4 abundances because, as you can see in this plot here, helium-4 is the species that is most sensitive to the number of neutrino species present during BBN. And so any deviation from standard BBN could manifest itself in the form of an additional neutrino species during BBN, and that would contribute to the total energy density at that time. So the way we measure primordial helium is to plot elemental oxygen versus helium abundance and extrapolate to zero metallicity for primordial helium abundance value. And I've indicated here where the low and lowest metallicity systems would be on the x-axis of this plot. And this is the primordial helium measurement made by Aver, Olive, and Skillman in 2015. And they measured primordial helium using a set of 11 BCDs. And this is probably currently the best method for measuring primordial helium because they included the infrared 10830 helium line, and I'll talk a bit about the importance of that line a bit later. But you could see the scatter in this plot is still pretty high. So what we need is a better sample of nearby BCDs, and we need lower metallicity systems at low redshift so that the extrapolation to zero metallicity is less of a stretch. And we need better data on these systems and a better way of analyzing the data. So we need to extend our observations to include the infrared helium line for all these systems, and we need to adopt a more sophisticated treatment in modeling these systems. So to increase the sample size of low metallicity galaxies, we've been using SDSS. So there are about 20 million galaxies in SDSS data release 12, of which we've cut down to 2,500 candidate BCDs. And we further cut that down to 250 candidate BCDs, which we are observing at Lick Observatory, and we follow up on the lowest metallicity systems using Keck. So each of these selection cuts are made on different criteria, the first of which is photometry, and the second of which is something I call morphology, and then finally based on the presence and strength of emission lines. So here's an image of LEO P in SDSS. LEO P is a local example of a low metallicity galaxy, and until recently it was the lowest metallicity system known. And so here's LEO P in HST imaging. You can see that it has a single H2 region, and it's been determined that it's ionized by a 25 solar mass O star. So based off the colors of LEO P and other BCDs, we queried SDSS for like objects. So here's a color plot of where our photometric color cuts lie and where LEO P is in this space in comparison to a set of other SDSS galaxies. So our systems are much bluer than any of the other galaxies in SDSS because they're dominated by the colors of their massive O or B stars. We also require that our objects are non-stellar in SDSS, so this yielded a total of 2,500 objects. So we looked through each of them by eye and isolated the ones and picked out the ones that are isolated. So we eliminated any H2 regions that were in spiral galaxies, for example. And we also required that there were bright knots present in these objects. So the two objects here on the bottom are two that we selected from SDSS. There's LEO-P again, so they have bright knots, which we think are indicative of an active star forming region. And we also require that there's an evidence for an underlying stellar population in these systems. And so we cut our sample of 2,500 candidate BCDs down to 250. So I've been leading a 28-night observational program during the past year using the CAST spectrograph on the Shane 3 meter at Lake Observatory. And our goal here is to obtain the O3 4959 to H beta ratio or the N2 6583 to H alpha ratio. And so for reference, LEO-P has an O3 to H beta ratio of 0.47 and an N2 to H alpha ratio of 0.007. So usually we don't detect the N2 lines at the Shane 3 meter, so we look to the blue side for an indication of metallicity. So here's a sample of 3 of our objects on CAST. So here you can see the H beta lines and the O3 4959 and 5007 doublet. So we follow up on a BCD at Keck if the 4959 to H beta ratio is less than 1. And so at Keck Observatory, our goal is to detect more lines, obtain higher signal to noise, and cover a wider or broader wavelength range. So we've been using LRES and NearSpec to observe our BCDs. And we require that we detect at least 5 optical helium lines as well as the infrared helium 10830 line. So here's a sample LRES spectrum of one of our objects. So you can see here that we do detect the N2 6583 line. This object has a N2 to H alpha ratio of 0.01. Here's the object on the blue side, so we detect 5 helium lines as well as this temperature-sensitive O3 4364 line, which is important when we model emission line fluxes. So I mentioned earlier the importance of this. Yes. Oh, sorry. I mentioned the importance of including the helium line. And so this is because the infrared helium line is the most density-sensitive helium line by far. And so in 2015, Aver et al. Tested the inclusion of this line in helium abundance measurements for their sample of 11 BCDs and found that including this line reduced the error in density measurements by 85%. And then this led to a decrease in helium abundance measurements by an average of 50%. And so I'm now determining the physical properties, so the electron temperature and density of our set of galaxies. And we will eventually measure elemental abundances, but especially with our Keck data, we have the ability to address some of the current issues with primordial abundance measurements. So current measurements use a theoretical scaling of the infrared and optical spectra. So with LRES and NearSpec, we will be obtaining continuous coverage between the optical and infrared for the first time. And we want to break the temperature density degeneracy in modeling emission line fluxes. And to do this, we will be adopting a method introduced also by Aver et al. In 2015, where they used MCMC to better model their emission line fluxes. So their model takes in 8 parameters, and they tested the effects of using this. They tested including the infrared helium line and adopting a temperature prior and its ability to reproduce helium abundances on a set of 1,000 synthetic spectra that they use. You can see that with the inclusion of the helium line and a temperature prior, they're able to reproduce the helium abundances pretty well. So we are working on increasing the sample size of low metallicity galaxies with SDSS and CAST. And we've obtained better spectra of these objects using LRES and NearSpec at Keck. And we will be able to better characterize the conditions and the abundances in these systems and hopefully provide a better constraint on primordial helium abundances so that we can test the standard model. Thank you.
There's time for a quick question. No? Yeah, sorry.
Are your objects large enough to get any spatial information, so you can see whether there's actual variation in the metallicities in the helium
So
across an object?
Yeah, I think the ones at the lowest redshifts we should be able to. So I haven't tried doing any of that, but we are getting AO time next week, so that we'll look at some of these objects and see if we can see if there's any differences in spatial helium abundances.
Any other question? Okay, if not, let's thank the speaker again.
Thank you.